a change of angle in a Morse circle here, in order to transfer that to reality, you need to divide it by 2. Or the opposite, if you go from here to here in the real sample, in order to transfer that to the Morse circle, you need to multiply by 2. And in this case, this is going to be the same thing. And what this is telling me is that going from this plane to that point, which is a failure, and it is that failure plane, I need to go this angle but divided by 2. So this angle is going to be now friction angle divided by 2 times 90 degrees divided by 2, or pi over 4.
Plus or times?
This is a plus. Right, 5 divided by 2. So I divide all of this by 2. Divided by 2. And I get this one divided by 2 and this one now divided by 4. So that angle over here now, if this is the point of failure, this is going to be the plane of failure. And this plane of failure is the plane of failure that you were also seeing in your experiments last week, right? Probably you will remember, we have some nice samples over here to show. I think I'm missing one product. Okay, no, I have. Yeah, someone stole one of my pieces of rock. Okay. This sample over here is this one over there. The failure is always at the characteristic angle that it is kind of a steep angle. Let's say that phi, which is a typical friction angle, is 30 degrees. How much is going to be phi divided by 2 plus 45 degrees? It's going to be 60 degrees, right? But let's just keep it just this 45, this 15, this is going to be 60. And that's an angle higher than 45, and it's always around this value. So it is in a steep angle. So now we can see how and why all these rocks, when they fail in shear, they fail at this characteristic angle. Why? Because it is the maximum, it is the plane with the maximum ratio of shear stress to normal stress. Okay, and we're going to do one more thing here, and we have time. I would also like to explain now why, or what is the ratio of sigma 1 to sigma 3. Because we're going to see later on that eventually that's what we measure, and that's what you're going to use also to compute some of these shear strength parameters. So my question is, what sometimes is called stress anisotropy? Sigma 1 divided by sigma 3. And in order to show that, we're going to use, again, the Morse circle. I'm going to call this point and this distance over here by C, and I'm going to call the radius of the Morse circle R. So if you know this, sigma 1 is C plus R, and sigma 3 is C minus R, right? So let me write that, C plus R and C minus R. But what is R as a function of the friction angle? Can you see that from trigonometry? If I know C and I know the friction angle, what is R going to be? Let me change the question. What is the sine of phi? R divided by C. Therefore, R is going to be C times the sine of phi. And if I replace this in here, then I'm going to have this, C sine of phi. There are C's everywhere. So finally, the maximum stress anisotropy for this uncemented sand is going to depend on the friction angle, and it's 1 plus sine of phi, 1 minus sine of phi. And let's say the friction angle is equal to 30. What is going to be 1 plus sine of phi divided 1 minus sine of phi? Well, you do those numbers, and let me tell you that this coefficient that Mr. Wheeler, right? Mr. Wheeler mentioned last time, 1/3 is very important. In practice, many times you're going to use this coefficient 1/3. But in this class, we're going to see where this 1/3 comes from and when it is not correct to use 1/3. But 1/3 is going to be a very important number, or 3 is also going to be a very important number. So, what is the sine of 30? Therefore, this number is going to be 3. According to this equation, the maximum stress anisotropy that an unsymmetric material can resist is about 3. So the maximum stress, sigma 1, has to be about 3 times sigma 3 if the friction angle were to be 30 degrees. Again, I'll have to measure again the surface of this, and I'll tell you exactly what that sigma 1 was. But you can see also that in the experiment that we did, that we calculated sigma 1 divided by sigma 3, which is 80 divided by 15, and which is equal to what? 4 point something, right? But not too far from what we would expect just from friction. So if we set the sigma 3 and we measure sigma 1, we can also measure the friction angle. So if I knew what this number is, also I can back calculate what the friction angle is. Okay, any questions about this? No? So remember, these are the basics of shear strength properties of uncemented materials. So let me write one more time here that if this line goes to 0, that means that this is uncemented. Okay. So if sigma 3 were to be equal to 0, no confining at all, what would be the maximum stress I can put on this uncemented material? In theory, if sigma 3 is 0, you are at this point. And if you are at that point, the maximum size of the circle is just going to be 0 too. Okay? Notice something else, which is very important. If I were to have a sigma 3 that will be bigger, let's say somewhere over here, if this is a new sigma 3, the stress, maximum stress I can apply, sigma 1 is going to be much bigger than that. It's going to be a much bigger circle. And sigma 1 is going to be somewhere over here. But if sigma 3 is 0, sigma 1 is going to be 0. And that is going to be valid for uncemented materials. All right, so what about now if we do have a cemented material, and we're going to do the same here. It's going to be sigma n, it's going to be tau, and now we have a cemented rock. And there is no confining from the sides. So somewhere over here, I'm going to run a test where I don't put any stress from the side. And I just load it. What is going to be the value of sigma 3? Of sigma 1? You already did this in the lab, and it had a name. The unconfined what? And is the unconfined compression strength equal to 0 for the cemented rock or not? If it's cemented, it's not going to be 0. So even if we have sigma 3 in this case equal to 0 for a cemented material, we can apply a load which is not 0. And I shouldn't have drawn that point, but just forget about a bit about that point. I'm telling you here in this experiment sigma 3 is equal to 0, so it's going to be a point over here. Okay? We agree about that. But even if sigma 3 is equal to 0 in a cemented material, still I can load it to a sigma 1, which is not equal to 0. And if this is a failure, we call that value sigma 1 the unconfined compression strength. If I were to subject now this cemented material to a confined stress, I'm going to see something similar to what I saw before. And that response is going to be dictated by the shear line that now is going to be equal to, notice that there is an offset. It's a number plus the friction coefficient times sigma n. It's not a line, but there is something else, and that something else is the intercept at sigma n equal to 0, and it's called cohesive strength. And it tells you how much the material is cemented. But notice that we still have this influence of frictional strength. And if I were, as I was saying before, now to use a non-zero sigma 3, again, the response or the failure Mohr circle of such rock, it will be something like this. So, one more thing over here, guys. You can see, even in the case of both cemented or uncemented rock, both of them, they get stronger as you increase the stress on them. And you guys should be the same. More stress, you get stronger, not weaker. Okay? You should be like rocks. Okay, I'll see you on Friday.